Now, Millikan, he did a turning point experiment, which was to work out the charge on the electron. So this diagram shows you the arrangement, okay? So this thing on the right-hand side here, this thing that you can hardly see on this right-hand side, this is an atomizer. So there's a little thing here that you can puff, and it puffs out little drops of oil into this top most part. And this container, well, you can change the pressure in it in most oil drop experiments, but let's imagine that it's just got air in it. So you've got all these little oil drops, and some of them are big, and you can see that in this diagram some of them are bigger than others, and some of them are absolutely minute. Okay, and there's a hole in this top plate, and the oil drops fall through because of gravity, their weight making them fall down. Okay, and there are various things that you can do. Right now, this thing on the left hand side, it's like a telescope. It's just an optical system, so that you can focus on these little droplets as they fall past the telescope, and the droplets fall. There's air in here, and or you can change it for different gases, but there's air in here. The droplets fall, and as they go past this thing, this is emitting X-rays. So as they go past, they get charged, and they get charged up negative. And now you can switch the X-rays off, of course, and in fact, in the first instance, that's what happens, okay? So there are no X-rays, the particles are just falling under gravity, but they don't fall very fast. First of all, the mass of each particle is tiny, and second of all, they're in a soup of air, and the air has a viscosity, not much, but it has a viscosity. And when you're got the mass of a tiny little droplet of oil, you end up reaching terminal velocity in your fall from here down to where the telescope can see. Right now, these particles are not charged at this point, okay? So all you're doing is you are looking at how at the particles, and you know that they will have reached terminal velocity, okay? So they're going at a constant speed. If they're going at a constant speed, they're in equilibrium, which means that if I exaggerate the particle, we can, for example, make that particle have two forces on it. There is the particle's weight, which of course is mg, and there is the drag force, the friction force, okay? Now, the friction force, assuming that the particle is going slowly enough that it's laminar flow, is governed by Stokes' law. And so this is the drag force on a particle, and it's 6 pi, this funny n thing, which is the viscosity, and that's the viscosity of the air that it's in. R is the radius of the particle, and V is how fast it's going. Well, as you watch it go past the end of the telescope, you can time it, and you know the view, the field of view for your telescope, which means that you can work out how fast it's going. Yay! Okay, so that's good. Right now, we also know what the density is of the oil density, right? And if you know the density of the oil, then you can use the mass of the particle is going to be the volume times the density. We know the density, right? Which means that if you can get V, you can measure V, and you know the density, then can you see that we end up with two different relationships, two different forces, which both of them depend on the radius, because the volume is of course 4/3 pi r cubed times the density. So this one depends on the on the radius, and this one depends on the radius differently. And so we can say that those two forces are the same. So we end up with 6 pi nRV is equal to 4/3 pi r cubed times rho times g, because of that g. And can you see that we can get rid of one of those because it cancels with that one? So if we know g and we know the density, and we know the speed and we know the viscosity, then we can work out what the radius is of the particle. And if we know what the radius is, we know what the mass is. So we can work out what the mass is, okay? And you can do it for lots of different mass particles. Right, so now we know what the mass is of our particle. Now, if for that same particle that we've just measured the speed of, if it's charged as it goes through the X-ray beam, and you apply a potential difference between these two plates, extra complication, right? If that's what you do, then your particle, you can get it to stop. Okay, so you can apply an upwards electric force which matches the downwards weight. Okay, and the electric force, of course, is EQ, which is also V over D times Q, right? And of course, again, those two forces are equal but opposite. So you can apply, so you have to measure the speed, and then you have to stop the particle by turning on the voltage so that you can keep the same particle, right? This is really hard. I've done this experiment. It's impossibly difficult, right? And then you can do V, this is the voltage now, that's a big V, not the velocity, the voltage times Q over D is equal to mg. And remember, we can get the mass from the velocity reading when there isn't a potential difference across. So you get the velocity and then you flick on the potential difference and you stop the particle, and then you have to turn it back down again because otherwise it will drift back the other way. And then when your particle is stopped, you can do VQ over D is equal to mg. But we know what m is, right? Which means that we can then get Q. Okay. And what they and that was the whole point of this experiment, okay? And what they discovered, what Millikan discovered, was doing this repeatedly over and over and over and over again. What he discovered was that the charges always seemed to be multiples of what we now call a unit charge. So not only did he discover that the charge on the electron, but he also discovered that all the electrons, they all have the same charge. So he discovered quantization of charge. And this was the first time we'd really discovered quantization of anything. So this was a turning point in physics.